Hey guys, this is Colin. In this video, I'm going to quickly go over some bolt, bolt torquing calculations that you'll probably need to do for future or CubeSat missions. And as I just finished learning the process and it's fresh in my mind, I figured I'd record a quick video about my learning process, and then hopefully, you guys can replicate it on your end. So first off, all the stuff that's been we're going over today is on the Coogan Space Wiki. So if you go to Coogan Space Wiki, go to home, scroll to the structure team, and then scroll down. You'll see section on bolts calculation selection. The topic we're going over, a lot of the formulas and data is being pulled from Greg's bolted joint analysis. So if you're more of a tech savvy person, we're mostly just pulling from this verbatim. But if you're anything like myself, like videos, this video will just kind of be a supplement to this. So what we're trying to do is we're trying to calculate the maximum force we can put on our bolt such that it's going to hold the two pieces together without destroying the threads of one of the pieces. So when you have like a part, like let's say on a CubeSat, you have a part that's threaded, and then you have like a plate on top that just has a hole in it, and then you put the bolt on top and you screw it into the threaded part, and then the bolt clamps it down. So you want to have the maximum force, that you want that bolt clamping with maximum force possible, but you want to make sure not to torque it too much, because if you end up putting too much, the bolt ends up putting too much of a force, it ends up actually stripping the threads that it's threading into. So what we're doing today is just doing the rough bolt torquing calculations to get you a rough ballpark about what numbers are kind of the maximum level that you should torque, or you should put your torque wrench at. But these are just rough calculations. You need to test all these numbers. This is just to get you like a general idea of what numbers you need to test. So to do that, we first to figure out what we need to torque the bolt to, we need to go look at the torque formula for, at least the rough one for our bolts. And you can find this one here by going down to calculating torque. It's a product of three variables. First variable is the K, or the nut factor. It's just kind of a random number that just kind of makes the numbers work. It's kind of arbitrary. I usually, for all these calculations, I put the K factor at 0.1 and then 0.3, and that gives me a range. But this is because bolt torque analysis isn't necessarily a science quite yet. We have a rough idea, a good idea how it works, but we're not as good at predicting as some other areas. So we still have to have this K factor in. So yeah, plug in 0.1, 0.3, as you'll see over here on this formula sheet that I have, that if we go to the Google Drive for Coogan Space, it's in structures testing. You can mess around with this number here on your formula sheet and just see what the torque comes out as. The next factor is just the nominal diameter of your bolt. So if you're using an M3 bolt, 3 millimeters. If you're using an M6, 6, pretty straightforward. F is the preload you want that you want to put on your bolt, or you want your bolt to be exerting between the two plates to hold them together. So for the preload, this is the part we actually have to go up and calculate. So going up here, basic preload. These are all the formulas we're looking at. For us, we want to look at the force it takes for the material to yield, as after the yield point, it's kind of hard to predict what the bolts are going to do. So we're going to worry about this FTY, but they're both the same. If you want to use ultimate tensile strength, go for it. So our first variable is STY, or the yield stress. This we actually determined experimentally, not the best experiment, but we did it by taking a kind of a load cell, placing one of our bolts in, or placing our bolt on one side, and then we threaded the bolt into a 3 millimeter aluminum threaded piece, which is the thinnest part of our satellite. And then we took the load cell and then we pulled the bolt that was stuck in the threaded aluminum part, and then we saw at what stress did the bolt slip and just pop right through the threads. So in our case, if we went to testing, M3 fastener testing, double click on combined data, these are all the results we got. So we scroll over here. Mostly the results we got was actually just doing a load cell on just the bolt itself. So that's gonna be way stronger than the actual connection between the bolt and the aluminum thread. But the number we ended up finding for the point at which the bolt slipped through the hole was 449 megapascals. Again, one data point. This is something future teams probably should run tests on in the future, but this is just the number we went to work off with. So going back to our formula, that's the yield stress. AT is the tensile area of the bolt. It's not. You can't just calculate with pi r squared for reasons you can read about down here. Basically, you plug in your nominal diameter of the bolt. In this case, M3. We're using M3, so it's a 3 millimeter. You plug into this formula, you get AT. You multiply that by your yield stress, and then you get, going back down to here, you get your preload. Then from your preload, you can multiply all this, and then you get the torque you set your torque wrench at. So that's what we're looking at here on this formula sheet here. We're running through a quick example. I was doing rough bolt torque calculations for a 3 millimeter bolt. So bolt size 3, stress to induce slip came from the combined data, which was 449 megapascals. Pitch is 0.5 millimeters. So from there you can derive the slip area and the force to induce slip. And then we have our nut factor. So our nut factor, assuming that the bolt is unlubricated or dry, you don't have any thread locker on it. These are the torques in Newton meters and pound inches that you expect for rough calculations. If you torqued it past this point, this is the point at which the threads would start to get destroyed, which is what we don't want. So we would actually want to choose a number on our torque wrench that's under this. We put it at 0.3. That's kind of the max range. But basically, the long of the short of it is these numbers are just rough estimations. Be sure to test them by drilling 8 holes, do the whole test setup. Yeah, this is just to get you a general idea of what numbers you need to test. So that's a quick crash course in the bolted joint analysis stuff that we did. Hopefully that helps. And if you need to find this Excel sheet that we put together, you can find it by going to the testing folder, and it should be right there.